Hey everyone, welcome back to 197 Concepts. In this video, I will be discussing with you how to create a RC Phase Shift Oscillator and its PCB. Okay, so let's jump into the video without any delay. So I hope you are familiar with RC Phase Shift Oscillator, but let's just take a brief recap or brief recognition of the circuit. Okay, so the circuit is basically has three RC sections, that is the resistor and capacitor sections, and each section will give you a phase shift of 60 degrees. And for us to get sustained oscillations, we need either a rotation of 360 degrees or 0 degrees, and definitely we need the gain to be greater than 1. Okay, so for getting the oscillations of 0 degrees or 360 degrees, what we are going to use is we are going to use three RC sections. From that, we are going to get 180 degrees, 60 degrees each section will make the rotation, or it will make a phase shift. So in that way, you get 180 degrees of phase shift. For another 180 degrees of phase shift, we are going to use a transistor or an op amp, okay, operational amplifier. So here what I'm doing is I'm going to use operational amplifier as our Proteus is not able to trigger the initial values. So definitely we know that RC phase shift oscillator or any kind of oscillator it will give an output or oscillations without giving any kind of trigger inputs. Okay, so here the Proteus is not able to do the minute simulations. It will calculate the very minute simulations or like consider the noise signals as zero in order to get a clear output. Okay, the program has been made or programmed in such a way. The tool has been programmed in that way. So for that, what we are going to do is instead of using a BJT or bipolar junction transistor, we will be using an op amp. So if you just look at the circuit diagram, what I'm going to do is I'm going to take an op amp. Definitely we will be using its power supplies. So this is minus VCC and this is plus VCC. Then we have the inverting input and non-inverting input. The non-inverting input is definitely connected to ground, and this inverting input is connected to the output via a feedback resistor of 3.3 kilo ohms. And to this, we will be having a feedback resistor also. So definitely this is the output. And this feedback resistor, what I'm going to do is instead of keeping a regular resistor, I'm going to keep it a potentiometer of 1000 K. So the circuit that I'm showing you here is limited to Proteus itself, because the Proteus is not able to do the initial calculations or the initial triggering of the circuit for the oscillators. I am increasing the feedback resistor value so that this resistor can create a huge load onto the op amp and simulate the trigger situation for the software to recognize that and generate an output. Okay, so I'm going to take up a potentiometer here of 1000 K, and since this is the output, just simply what I'm going to do is I'm just going to connect three RC networks in this manner. This is the resistor. Again, this is a capacitor and a resistor, and then a capacitor and a resistor. So all these three will be connected to ground, and this output will be taken back and connected to the input. Okay, finally what I'm going to do is I'm just going to keep here an oscilloscope and check the output. So this is our circuit, and yeah, the values are 6.8 kilo ohms, 6.8 kilo ohms, 6.8 kilo ohms, and 0.01 microfarads, 0.01 microfarads, 0.01 microfarads. So this is the complete circuit. Now what we have to do is we have to check the calculations and the oscillation or the frequency of oscillations. Okay, so theoretically what we are going to do is we are going to calculate it, and the formula that we know for the calculation is F is equals to 1 by 2 pi RC square root of 6. So again, here I'm going to substitute the value. So the only thing that I'm going to consider is this capacitance values, all three, and then the 6.8 resistor values. There is no need to consider these values, okay? Only the RC section is considered. So for that, I'm going to substitute the values here. So it's 1 divided by 2 pi root 6 into, so the R value, the resistor value is 6.8 into 10 cube. The capacitor value is 0.01 into 10 to the power of minus 6. So yeah, this is the value. And if you rearrange these all, so 2 pi square root of 6 into 6.8 multiplied by 0.01 multiplied by 10 to the power of 3 minus 6. So we need the calculator here. Let's do this side by side. Okay, it's better if I change this way. So the very first thing that I need is 6.8 multiplied by 0.01. That will give me a value of 0.06. So let us write that value here. So yes, F is equals to 2 pi root 6 into 0.068 multiplied by 10 to the power of minus 3. It is on the numerator. Now what I'm going to do is, since my denominator is having a 10 to the power of minus 3, when this goes up, it becomes 10 to 10 cube and 2 pi root 6. So 2 into pi is 22 by 7 multiplied by root 6 multiplied by 0 point multiplied by 0.068, and this can be again expanded as, so just 2 multiplied by 0.068, this will give you a value of 0.136. Okay, so 0.136, it's causing trouble. Okay, so this will give me F is equals to 10 cube 0.136 multiplied by 3.14 multiplied by root 6. So that will again, so 0.136 multiplied by, so 0.136 multiplied by 3.17. So it's 0.43112. 0.43112, here 10 cube multiplied by root 6. So the value of root 6, for that, yeah, we need the scientific calculator. So square root of 6, no, it's a square root. Square root of 6 is 2.44 multiplied by 2.44. Again, that will be 10 cube divided by, so yes, standard calculator, 2.44 multiplied by 0.43112, 0.43112, it will be 1.05. Okay, so 1.05, so 1.05, no, 1 divided by 1.05 will give you, hmm, So I might have made some mistakes here. So yes, this time I'm going to use my phone calculator. So f is equals to 1 by 2 pi root 6 RC, which is equals to 1 by 2 into 22 by 7 multiplied by root 6 multiplied by 6.8 into 10 cube multiplied by 0.01 into 10 to the power of minus 6. So f is equals to 1, 2 into, first of all, 22 by 7. So let us resolve these. So 22 divided by 7 will give you, yes, 3.14. It's a correct value, 3.14 multiplied by square root of 6. So square root, where is square root? Yeah, square root of 6 is 2.44. So this is also correct. 2.44 multiplied by 6.8 multiplied by 0.01 multiplied by 10 to the power of 3 minus 6. So f is equals to, yeah, so 2 multiplied by 3.14 will give you a value of 6.28. 6.28 multiplied by 2.44, I am keeping it as it is. Then 6.8 multiplied by 0.01 will give you a value of 0.06. 0.06 10 to the power of minus 3. These are all in the new denominator. Now f is equals to, so 6.28 multiplied by 2.44 will give me 15.3232. So 15.32 multiplied by 0.06. So this 10 cube will go on the numerator. So that's 10 cube divided by 15.32 multiplied by 0.06. It's 0.9192. 0.9192. Now 1 divided by 0.9192 will give you a value of 1.08 into 10 cube. So this will give me 1.08 kilohertz of frequency. Now keep this frequency in mind, because when we do the here practical calculations using the oscilloscope, we should get a value that is near to 1.08 kilohertz. Okay, so yes, now I'm going to open Proteus. So here I'm going to create a new project. Just click on browse, selecting the path. So on the desktop, I'm going to keep this as RC Phase Shift. Okay, select the folder, and the project name is RC Oscillator. So without any changing things here, I'm just clicking on finish, and here the thing that I need is 741 components, and I need a resistor, a capacitor also. That's it. Those are the three things that I need. So just a capacitor 1, capacitor 2 for 3 RC networks. I'm changing the values to 0.01 microfarads. Just copy this value Oh, and paste it like this. Okay, so just connect all these three, and I need three resistors also. Actually, I need four resistors, not registers. So the value of each resistor is 6.8 kilo ohms. Yes, and I need these to be connected to a proper ground. So terminal, just take the ground and click it here. Okay, now coming to our 741, this is placed here. Oh yeah, it's better to make it y-axis mirror because we get the number 3 pin here. So this can be grounded here, and then in the power generator mode we need DC signals, two DC signals, as this thing need power supply of plus 15 and minus 15 in order to operate. So this is plus 15 and this is minus 15, and yeah, we need a feedback resistor which is a potentiometer, but before that I need to place a resistor here of 3.3 kilo ohms, and this has to be given to the feedback of the operational amplifier. Okay, not the feedback, the output of operational amplifier. Now I need a potentiometer pot. So potentiometer is placed right here. Take a part of the output and connect it as the input, and this one will be connected like this. So these are the connections, just these are the connections, and yeah, I need an oscilloscope also to check the output. Okay, now when I run this, initially I won't get any output. Okay, but when I make some changes here, oh yeah, I forgot to change the value of this potentiometer. It's just 1K. That's why the output is not coming. You have to keep it 1000K. Okay, now let's check it once. So no output. You are getting the output, but it's not a proper output. Okay, so we have to do some changes here. Mm, actually, I'm checking the input of this op amp. Yeah, I was checking the input of the op amp. So this is the output, right? So this is the thing that we have to check. So this RC sections should come at the input side. So better what I will do is I will just simply disconnect all this, even this one also. I will take this section and I will move this section to the back of the circuit like this. So this will be much easier to understand. The only thing that you have to keep in mind is this is a separate biasing, what we say, uh, biasing resistor for the op amp. So that should be not taken into consideration while calculating the frequency. Okay, so only up to R3. Then this will be connected in this manner, and finally this is connected to oscilloscope. Now when you run this, yes, you have to change the values here. You have to make some changes here. Only then you will get the output. The inverting input is the non-inverting input is not connected to the ground. Yeah, there you go. You get an output, and now we have to calculate the frequency of this. So there is no way to expand it. Instead, I will just off all those others. I will bring it in the center. Okay, and I will expand the time period. So let us take one complete cycle starting from here. So 1, 2, 3, 4, 5. It's 5 and something. Okay. So yes, 1, 2, 3, 4, 5. That's a total of 5 boxes horizontally. And each box is of 2 milliseconds. Okay. Now when I come here, I have I have covered I have covered 5 units each of 0.2 milliseconds. The total time period T will be 5 into 0.2 milliseconds. So this will give me 1 millisecond. Now we know that frequency is equals to 1 by T, and this will be 1 by 1 milli. So that will be 1 by 1 into 10 to the power of minus 3. So 1 by 1 into 10 to the power of 3. That will be 1 kilohertz. Okay. So yes, uh, theoretically I should get 1.01 kilohertz, but practically I'm getting 1 kilohertz. So that's not a big deal. So our output is correct. So yes, we can proceed with PCB. But before going for the PCB, we need to do some changes. Those are nothing but keeping some points to get the output, and to what we say, to give the power supply to the 741 op amp. Okay, simply what I'm going to do is I am going to save this project as RTP ready to print. Click it on OK, enter. And in this, what I'm going to do is I'm going to remove this and this one also and this one also. Instead of that, first of all, I have to check my potentiometer is having a footprint or not. No, this is not having a footprint. So yes, practically going, you get the value of you can place a resistor itself. So simply what I'm going to do is I'm just removing this also, and I'm placing a resistor like this. And I need 2-pin headers, 2-pin header. Along with that, I need 1-pin headers also. So 2-pin headers, one header will be placed here, and the other pin will be connected to the ground. Its name will be out to check the output waveform. Now the 1-pin header, just place it there, minus and plus. Okay, so yes, I believe this is plus VCC, so plus 15, and this is minus 15. In order to verify this, simply delete one and one pin header, place one DC signal and connect it. If you get plus VCC, yes, that's the correct thing. This is minus VCC. So this is the right one. So that's it. Those are the changes. Now I will directly jump into our PCB layout. Yes, after jumping here, the very first thing that I'm going to do is I'm just going to place a box here. So board edge like this, and I'm going to auto place all my components. Yeah, these are the components that I need. Just paste them all, and now I'm going to arrange them. So rotate clockwise, drag it and keep it in the middle. So these two things, the plus VCC and minus VCC, these has to come and stay at one specific point. Yes, now I need to check the output. Where is that out? Out, yeah, here it is. This two pin header is used to check the output, and the other thing, yeah, I will keep this a little bit apart here because I need R1, R2, R3. So very first thing, C1, I need to create this section, right? So C1, C2, and C3. Yes, in the same way, R2 and R1, and finally the R3. So R5 is a feedback resistor. So just I'm going to keep it here, and R4 is our input resistor like this. Okay. One thing I should do is I should define the power rails. So for that, this is mains and terminal mode, select ground, do this and power. Now let's check the PCB layout. So mains, yes, there is mains. So it is only for ground. There is no need to give the power supply for this. So in that case, why do you keep this separate component like this instead of this? Simply what I'm going to do is I'm going to take a one pin header delete this, and I'm going to keep it just like this here. It's going to be renamed as ground. So PCB mode ground, and the ground connection I'm just keeping it here along with this. Okay, that's it. Those are the connections. I mean, those are the placement of the components. Now I have to do the connections. So simply what I have to do is I have to just go into the track mode. Now I have to start connecting the components. So yes, the very first pin number 1 is going to be connected to the output of PCB, I mean 7205. Before that, I'm just going to yeah, I've selected the bottom copper, and now I'm going to connect one by one. So this one and this one, I'm connecting as per my circuit diagram. So this is easiest one. You just need to have an idea of where you're doing connections or where you're passing all the connections and all. And yes, that will do the trick. Yes, finish. These three has to be connected to the ground. Yeah, and the R4 is connected to pin number 2. So R4 is connected to pin number 2, and this pin number 2 is also connected to the feedback resistor again, and the output is pin number 7, I believe. No, it's pin number 6. So pin number 6 is gonna be connected to two components. One is the feedback resistor, the other is yeah, checking the output one. And the ground has to be connected in this way. Of course, pin number 6 is the connection, and pin number 3 should be grounded. So I am going to connect it in this way. Okay, and minus 15 should be connected to pin number 4, and plus 15 should be connected to pin number 7. Now the only thing is the feedback path. So for that, I am gonna make a roundabout here, and going to make a connection just right there. Okay, so this is the whole circuit of PCB. So if you check this in 3D visualizer, it's loading. So these are the components. So these three capacitors resistors are the feedback so phase shift sections, and this is the input resistor, feedback resistor, our op amp, and these are the input and grounds, power supply, and from here this header pin we are going to check the output. The connections are at the bottom side. Okay, so since I've used the bottom copper, so connections are at the bottom side. Now simply what I'm going to do is I'm going to click it on output, print layout. So select the printer as PDF. I don't need top, I need the top silk. I don't need top copper, top resist, and bottom resist. I just need those three things. And yes, that's it. Click on OK. So it's RC RTP ready to print. And it might have created a graph here. is RCRTP. So that's it. This is our ready to print here. Okay. So hope you have understood the experiment, and that's it for this video. See you in the next video. Thank you.